live stream. Okay.
So, good evening, everyone, and welcome to the fourth lecture of the STEMS 2022 final camp. Today, we're very delighted to have Professor Ruta Mehta with us. Let me start with a brief introduction. She's an assistant professor in the Department of Computer Science at the University of Illinois in Urbana-Champaign, and her primary research interests are in economics, game theory, and computation, and fair division to add. So she completed her PhD from IIT Bombay, and she's also a recipient of various awards, including the NSF Career Award in 2018. Today, she'll be taking us on a journey through fair division of goods and how solutions from economics achieve some of the best in fairness and efficiency. So before we begin, just a quick reminder, put your questions in the chat box or use the raise hand option and we can take it up appropriately. So without any further delay, over to you, Professor Ruta Mehta.
Hi everyone, and again, sorry, there was some issue with my laptop, and yeah, Windows, you know, right? It starts updating at the exactly wrong time. Okay, so let's get started. This is the topic is sounds like should be quite accessible. If there are questions that are something is not clear, please feel free to ask. So I'll start with something that is kind of more not as much technical, but probably I'll at the end for some of the audience who might be interested in technical stuff, I'll go like a little deeper into the technical stuff. So if something is not clear, feel free to ask. Okay, so Amik, if there are questions that are kind of needs my attention, please let me know. Okay, thank you. Okay. I'm just trying to, okay, anyway, hide this panel if I can. Okay, anyway. Okay, so here is the problem I'm posing to you, that I have some set of items. Okay, let's say land, it could be bread, milk, it could be house chores, it could be teaching duties. Okay, so it's a mix of something that people like, and it could be that something that they don't like. So they don't want to do any, let's say, housework, but they would be happy to maybe take a bread. And the other property is that these are all divisible. So you can divide them. If I give you a loaf of bread, you can divide them into pieces and then give it to different people. So these are like divisible items, and you want to allocate these items to these people, and they are different type of. So somebody likes bread, somebody likes milk, somebody may say I want a whatever, like cheese, whatever, right? So and you want to do it in a fair and efficient manner. Okay, so I will tell you what fair and efficient is like more formally, but before we do that, let me just briefly tell you why I care about this problem. Well, if you want to allocate, let's say, landing slots or some resource, such type of resources like gates, landing slots to aircrafts when there are weather-related delay, basically you can't kind of charge them to the airlines because you have already charged the airline a priori. So when you do reshuffling, you can't charge them. So then how do you do this fair and efficiently? In US and at many places, schools, most of the schools are public, and when you want to assign seats, and different schools have different kind of expertise, if you wish, and if they want to assign school seats to, let's say, students, they have to be fair when they do that. A vaccine allocation, which vaccine, how much quota of vaccine should go to which state or which which areas in the state. Again, you have to be, because there is no money charge as such, government has to be fair about it. Kidney exchange, another example, where money is a completely unallowed thing, like it's unlawful to do any type of kidney exchange with money. So, I mean, in all of these settings, you can't charge money. And so whatever allocation you want to make has to be fair. Um, because if you can't charge money, you can't ask. Yeah, I mean, we will see if you can charge money, then you can set up a market and um, you can do allocation with that, and that will be fair. But wherever you can't charge money, you have to be somehow explicitly ensure that your allocation is fair. Okay, so a little bit of formalism. So the model is formally, let's say you have set A of agents and set M of divisible items. Okay, and because these items are divisible, I can think of them as just supply of one unit without loss of generality. Because if you give me, let's say, 1 kilo of cheese, um, or let's say 10 kilo of cheese, I can think of 10 kilo, give it some name, let's say, I don't know, XYZ, and then think of 1 unit of XYZ. Okay, so it's equivalent to think of in the divisible case, you can kind of, it's without, you can always change the numerator, right? So either you measuring things in, let's say, rupees or dollars. As you go from dollar to rupee, you increase the money. But when you individually measuring these things, you can just, so basically you can give new name to whatever the quantity is, and then think of it as just one unit. And it is typically assumed that the valuation functions are concave. What is concavity? It is basically capturing decreasing marginals. So imagine I give you, let's say, one ice cream. I don't know, whichever your favorite one, chocolate. You are very happy. Okay, then I give you a second one. Will you be as happy as the eating the first one? Maybe, maybe not, right? Happy, but not as much as you eat the first one. And then I give you third one. Oh no, you would say no more. I'm kind of done. Maybe I can eat third, but so what I'm trying to say that every extra ice cream, the happiness that you get is going to be decreasing, right? So that's why it's the concavity exactly captures that problem. Okay, and then we want to find fair and efficient allocation. So let's do a thought experiment to understand what should be fair and what is efficient. What do we mean by this? Here. So let's say we have these two people, okay? Let's say Raj and Geeta. And they both have this half moon cookie. Half of the cookie is chocolate, the other half is vanilla. Okay, so this black part is chocolate, the white part is vanilla. And Raj doesn't care. He likes both chocolate and vanilla equally. But Geeta, she hates chocolate. She only likes vanilla. And so how should we divide the cookie between them? Okay, so imagine they are trying to divide the cookie between them. And let's say I give you these three possible partitions. So the red line tells you what should be the partition. And the character, let's say the B side goes to, okay, so this was like Alice and Bob, sorry, but yeah. So let's say B side goes to Raj and A side goes to Geeta. What do you think? What's your thought? Which one should be the good outcome? Let's say outcome one fair, where I just divide equally the chocolate and vanilla between the two. Is it fair or is it not fair? Any thoughts? You can speak up. It's okay.
There is a not a fair saying it's not fair, and there is a that saying it is fair, but not optimal.
Good. Yeah, good point. So it is fair. I mean, you can't say it's not fair because both of them are getting equal amount of both, right? Like, what more fairness do you want, right? Like, in some sense. But it is definitely not optimal, right? Is two fair? If you ask individually to both of them, are they happy with their part? Or they want the other's part? They would say, yeah, in the two, they will say we are happy, right? Because Raj is indifferent So he doesn't care. He just wants half of the cookie in any manner, right? And Geeta is happier because she gets like more of vanilla, and she likes that more, right? And in that sense, third is still fair. So although it seems like you are not doing the division properly, from individual's perspective, the third outcome where we give all of the chocolate to Raj and all of the vanilla to Geeta is still fair from the Raj perspective because he doesn't care whether he gets chocolate or vanilla. And from Alice's perspective, she is the happiest, right? Like she's thrilled because she got all of vanilla that she liked the most. Right? So the point I'm trying to make is that you can have fair outcome. First of all, what should be fair is not obvious, right? Like how should we define fairness is not obvious. So there are multiple definitions. And the secondly, fair need not be efficient. Okay, fair need not be an outcome which is kind of optimal with respect to everybody. Okay, so in that sense, definitely third is much more optimal and fair than the first outcome, right? Okay, so with this example in hand, let's start formalizing things a bit more. Okay, so now I'm going to tell you a bit about different efficiency and fairness notions that are kind of used. I'm trying to make sure this panel, yeah, okay. Okay, so first and kind of most basic fairness notion and most important one is envy-freeness. That is, no agent envies others' allocation over their allocation, right? So in this example, if I give half to both of milk, bread, and cheese to both, let's say, Geeta and Raj, then it's envy-free because both of them gets the same amount. So if everybody gets the same amount of every item, then it has to be envy-free because everybody has the same allocation, so nobody can envy others' allocation, right? The other is proportional. Proportional meaning that every agent gets at least average value, essentially. Okay, so if let's say VI is a valuation function of agent I, and M is the set of all the items, then look at the value that they get by consuming all of the items and divide it by the number of agents in the system. So this is kind of, they got average value of the entire grand bundle. Okay, so now if I do this half for this milk, bread, and cheese for Alice and Geeta and Raj, then that's not going to be proportional. Do you see why? Or is it going to be proportional? Sorry, in this example, 4 plus 3 is 7, and they get, yeah, they're going to get half. So yeah, okay. So this half is also proportional. Okay, in this case. But if there was one more agent, I could create an example where just doing like this naive equal distribution is not proportional. Okay, in the efficiency where we want to be like more like give items that people who like more, give them more of that, like in the chocolate vanilla example. So okay, so giving equal amount to both of these guys is not Pareto optimal, okay, because Alice likes milk more while Raj likes cheese more. So you can think of what would be a Pareto optimal allocation here. Actually, the milk, all of milk should go to Geeta, and all of cheese should go to Raj. Okay, and you will see you will have to divide the bread somehow to get, let's say, if you want to ensure all three together. So what we will try to do is we want all the notions, we want to ensure all the notions together, and that's the main difficult part. And there is something called welfare maximization. So typically welfare maximization means that you just maximize the sum of the values that individual agents get. That's the welfare. That's called the welfare of the society or the system, right? But here, if you try to do this, you will end up giving everything to Raj because he is kind of really positive or enthusiastic person who thinks everything very highly, right? You see these people, right, who are very hyper, who like, yeah. And then there are people who are like very mellow, yeah, fine, okay, types. So that's like Geeta, and that's the other person is Raj. So somebody who's very enthusiastic, and if you ask them, they might be tell you that yeah, really like this, and if you can end up giving everything to them if you just maximize welfare. But Nash welfare is maximizing the product of the values. And if you do maximizing product of the value, we will never give everything to one person because the other person will get zero utility. And zero multiplication with anything is a zero, right? So product forces you to kind of really do like a little bit of equal or fair division. And it turns out that this notion of competitive equilibrium that I'll just define achieves all of these together and something more. Okay, so there is one solution concept that achieves all the guarantees that we care about together. And this is very, very peculiar for the divisible items. If you go to indivisible items, everything breaks. So it's very nice that there's this one notion that can achieve all the guarantees together that we care about. Please, okay, keep track of time, okay? Because yeah, I'm not keeping track of time. Okay, okay. So let me tell you what competitive equilibrium means. So you can also, the other name for competitive equilibrium is market equilibrium. Okay, so basically we have to talk about markets. Okay, so imagine a market in a traditional setting. There are a set of agents or buyers, if you wish, who come to the market and they have some likings. They say, I like cheese, you may like milk. We go to grocery store, or let's say in our local store to bakery and trying to buy stuff, right? And then when we go to a bakery or any such place or grocery store, we will see what costs what, the prices, right? So then based on the prices, I will decide, oh, I have only $10 or 10 rupees. So I don't have money to buy enough cheese. So I'll probably go ahead and buy bread because I'm really hungry. I want to eat something, right? So based on my utility function and based on what money I have, I will decide what to buy. Okay. When every agent does that, when every agent, they decide their optimal bundle, it's called optimal bundle, based on what their utility is, based on how much money they have, they decide what to buy. That bundle that they buy is called optimal bundle of those agents. When all of them decide the optimal bundles or buy what they like, supply should be equals demand. Okay, so this is also called, because this is going to give you demand for every each of these items, and at competitive equilibrium, demand should be equal supply. Okay. Okay, so we say that the prices are at competitive equilibrium if demand equals supply. Okay, I'll be back in 1 second. Okay, 1 second. Okay, okay. So is the notion clear what competitive equilibrium is? Okay, it's basically a set of prices, and for us it will be a fictitious. This will be fictitious prices. Okay, but still set of prices. Okay, such that when every agent at these prices buy their best bundle, their most like bundle based on however money they have, demand should be equal supply for every item. Okay, so every item should be completely sold, and there should be no over demand. So it should not happen that, oh, I wanted 2 loaves of bread, but there is only 1 available. That should not happen. Okay, so when I decide my demand, I don't think about how much is available. I just ask, I want 2 loaves of bread. Do you have it? Okay. Okay. Okay, and we say that competitive equilibrium with equal income if we give exactly $1 or 1 rupee or let's say 10 rupee to every agent to buy. Okay, so when every agent has exactly one same amount of money to spend, then we say that it's equal income among agents. So basically what we are doing is we are giving equal buying power to all the agents, and then we are asking them to buy, okay, after setting the prices. Okay, so okay, what are the properties? So you can immediately see that the outcome or the allocation from the competitive equilibrium has to be envy free. Do you see why? Okay, so there is a question: if supply is greater than demand, they will be able to buy an optimal bundle. Is that no? So if there is more supply than demand, then there are some items unallocated, and so that's not a competitive equilibrium. Okay. Okay. So do you see why this is envy free? Well, you have $1. I have $1. We bought what we liked. I bought what I liked, which is, let's say, bread. I could have bought your bundle because I have same amount of money as yours, but I didn't. Why? Because I like my bundle more than your bundle. That's why it's envy free. Okay. And in the divisible case, when you have envy freeness as well as the fact that everything is allocated completely, you get automatically proportionality. Okay, you can think about it why. And then there is a first welfare theorem from economics that tells us that the allocation has to be Pareto optimal, essentially because everybody is doing what they want to do, what everybody's buying what they like the best, right? And everything gets completely allocated, right? That's why essentially you get Pareto optimal. It's not very difficult to see, but it's not trivial either. Okay. And there is a long line of work within economics to understand existence, computation, properties of competitive equilibrium. Okay, this is kind of bread and butter in some sense of economics. I told you about very stylized model and equilibrium in that, but people have thought about this competitive equilibrium, much more complex models within economics.
Okay, any question? Question in the chat. So you mentioned that all four conditions, that envy freeness, Pareto optimality, and those can be fulfilled for divisible items, but for indivisible items, it all breaks. So what are some indivisible items, and when would we care about distributing them if they're not divisible?
What are some indivisible items, and when would we care about distributing them if we are not divisible? Oh, lots, no? Like you can say let's say land, like a typical example, land, right? Satellite time. Okay, so if you, let's say, have satellite and countries or regions are trying to share its time, anything that relates to like time, land is divisible, right? You are so that's divisible. Suppose you are trying to divide the cost of some kind of let's say climate resilience. I'm taking really high level examples, okay? And there is some cost to it, and the countries want to divide the cost among themselves. How should they divide? What's the fair way to divide it? Okay, so yeah, I mean, I think even teaching duties are in some sense divisible, because it need not be that or let's say TA duties, right? Like it's a time that you are dividing basically, right? So yeah, lots and lots of examples actually. And the land division comes in dividing, let's say, rights for maybe mining or taking out oil, or yeah. So yeah, and if you want to eat cake, you have to divide a cake. Okay. So there are lots, and there is like, because this age-old topic within economics, amazing amount of work when all the items are goods. Okay. There are convex programming formulations, really fast algorithms, provably fast, non-provably fast, simplex-like algorithms, meaning algorithm that just follows a path on some polytope. Okay, and in some cases the problem is pretty hard, and formally we can prove that there cannot be really fast algorithms for these cases. So the point I want to make in this slide is that it's extensively studied topic. Okay, but with chores, when you have chores together with goods, like teaching duties again, or house chores, right? Even house chores is divisible in some sense. I can say that I'm going to do half of this room's pocha and you are going to do the other half. Okay, I'm going to mop this half of this room and you mop the other half. So that's divisible. Okay, so yeah, so when there are chores, how do you define a competitive claim? First of all, it's like almost similar, but for chores, I can't ask you to, let's say, you do this chore and you pay one rupee or 10 rupee or something. That's not going to happen, right? You're not going to do pay me for doing chores. So I have to pay you for doing chores. So the payment is going to reverse. The other everything else is the same. Okay, so I post prices on the chores saying that if you do this 1 unit of this chore, whatever 1 unit mean, okay, I'm going to give you 15 rupees or 5 rupees or 500 rupees or whatever, right? And then you decide which chores you would like to do based on your earning requirement. Now you have earning requirement that I have to earn so much, and based on that you will decide what chores you want to do, right? And again, based on everybody's demand, then we check whether for every chore demand equals supply or not. And if it is, then we say that the payment scheme that I posted on these chores is at competitive equivalent. And we say that it's competitive equivalent at equal income, and every agent has to earn exactly same amount of money. Okay, so let's say exactly $1 or 100 rupees or whatever. Okay. So is the setting with chores clear, like how it separates from the goods? Okay, there's only one particular point where it separates, and it's just the payment reverses. Okay. Okay. And what happens when we have goods and chores both? It could happen that, so I want to consider mixed setting as well, right? When you have goods and chores both. Well, for goods, you have positive prices. For chores, you have negative prices. Negative prices meaning payments. And exactly still the same thing. How do you find equal income here? That's tricky. Okay. And let's not go there, because finally you have to kind of see whether it's a positive market or is a negative market. If it is a positive market, whatever that means, I'm not formally defining it, then you will give one equal amount of money to people, to the agents to spend. And if it is somehow a negative market, then you ask them to earn $1. Okay, so let's not go there. But what I want to tell you today is mainly about the topic that is not as well studied, basically how to handle chores. So once we understand how to handle chores, we can handle chores and goods together mixed. Okay, so pretty recently people started thinking about this compared to the goods case. 2017 is not very recent, but still compared to the goods case, with hundreds of years people have been thinking about it. So they said that if valuation functions are one homogeneous, which includes, let's say, linear. So whenever I say one homogeneous, just think about linear functions. Okay, what is a linear function? You kind of, the very initially the functions we saw for this Raj and Geeta, where they have value specified for each of the items individually, and if you give a bundle, then you just sum up those values. Okay, so let's say let me just take one example so that it's clear. Okay, so here it's 322. What does that mean? For Geeta, milk, bread, and cheese gives happiness of 322. And if I give her milk and bread, then her happiness is 3 + 2 = 5. That's linear. That's it. Okay. Okay. So they studied this problem under one homogeneous, and so we started with concave. One homogeneous is a subclass of that, which contains really important classes that we really care about. CES is a constant elasticity of with substitution, if you know about it, and then linear is another class that we really care about. So it contains all of that. So it's a superset of that. They give a nice characterization for CEI, but through this characterization, they also showed that the set of solutions is non-convex. Okay, even if there are only chores and no goods in the system. Okay, in contrast, for goods, there are convex programming formulations for this problem. So we know that CEI set is convex, and there are really fast algorithms, strongly polynomial, meaning let's just stick to polynomial. That they are very really fast algorithms. So whenever we have non-convexity in the solution set, it becomes kind of tricky to get polynomial time algorithm. First of all, whenever you have a convex set, you can try and think of some potential functions that go to that set. But when you have non-convexity and disconnectedness, right? Immediately it seems like the potential function type of method is not going to work, and then this any type of like convex programming, linear programming, this type of techniques kind of goes out of the window, right? Because generally they all follow some potential. Okay, there were work when some special cases, number of agents or items are constant, but people really struggle to go beyond that. So typically these algorithms are all enumerative. They somehow enumerate some kind of configurations, and for each of them check whether the configuration gives us the solution or not. So these guys, this was a really remarkable paper. They noted that because of this non-convexity and disconnectedness, we expect that the computational the problem is going to be computationally difficult. Okay, so they kind of expected that there might not be any polynomial time algorithm. So then we asked, even is approximation possible? What does approximation mean? So remember, in equal income, I give exactly same amount of money to everybody. But suppose I perturb it a little bit. You get, let's say, 11 rupee, I get, let's say, 10.5 rupee, and somebody else, let's get 9.5 rupee instead of 10 to everyone. Okay, so I'm allowing some kind of approximation in the amount of money that I kind of ask every person to earn. So then, so what we show is that we only, let's say, I'm just giving you result for only chores and linear valuation. We give an exterior point method. So the kind of highlight of this result is this new method. It is called exterior point method. Through this, we compute approximate CEI. Okay, where only everything is exact, only that the money people has to earn need not be exactly one. It could be 1 plus epsilon or 1 minus epsilon for some epsilon, which is polynomially small, pretty small. We show that this extends to one homogeneous and two mixed manner. And this method in particular is generalizable to coordinate wise monotone functions. Okay, so that's the thing I want to convey. How much time do I have?
So about half an hour into the talk, maybe like another 40 minutes, maybe around
40 minutes. So I have 20 more minutes.
Yeah, around maybe like half an hour more, around 30 minutes.
Okay. So we have, so again, let me just, because now we are going into formalism. Okay, so now let me just put a disclaimer. We are going into now more math. Okay, so let me now start putting symbols. Okay, so let's say A is the set of n agents. Each agent has to earn exactly $1. Okay, and M is the set of chores that we want to divide. These are divisible chores, and every chore has 1 unit. So there is 1 unit of every chore available. The agent's valuation functions are linear. That means if I give xij unit of chore j to agent I, then her value, okay, is Vij. Vij is going to be negative because these are pain, okay, disutilities, because these are chores, okay. So Vij is the pain they so this Vij is utility, but minus of that is the pain they get, because these values are negative, and it's easy to intuitively think of these are disutility. So I'm going to convert it to Tij, meaning disutility, or the pain that agent I gets from this chore, from consuming unit amount of this chore. Now, when I say that an allocation, because I assume that there's exactly 1 unit of supply available for every chore, I say that an allocation is feasible if every chore is allocated exactly in 1 minute, when I decide the allocation for each of the agents. Okay, so you sum up how much for every chore J, sum up how much every agent gets over all the agents. That this is basically how much I allocated of this chore. It should be exactly equal to the supply, 1 unit. Then I say that this allocation is feasible. Basically, supply equals demand type of allocation. Okay. Okay. So these guys showed that if you want to find complete equilibrium, solve this program. Okay. So you are minimizing product of the disutilities of the agents, subject to the allocation should be feasible. Okay. Exactly 1 unit of every chore is allocated in total, and the disutility of every agent should be greater than 0. So if they don't put this extra constraint, non-zero constraint, then very easy, right? You just not give anything to one agent, that's going to make that disutility 0. Then you can give whatever to any other agent, the product is going to take care of everything, right? Then the product is always going to be 0, right? So that's why they put this extra constraint, and this is an open constraint. That's a difficult one. Okay. In contrast, for goods, when you try to solve the problem, there's a remarkable similarities. It's called Heisenberg-Gale convex program. Okay, you maximize the product. That's it, and you don't have any this greater than 0 type of constraint. That's it. Okay, so exactly same. Instead of minimizing, you maximize. That's it. Now I can take logs on both sides. So if you take a log of, let's say, A times B is what? Log of A plus log of B. Right? So when you apply log is an increasing function, right? It's a monotone function. So I can safely apply logs and still the problem is going to be the same. Okay, so I apply logs on both sides, on both programs. Okay, and this is what I get. Okay, so here you are maximizing sum of the log of linear function. Log is concave function. Log of linear is going to be concave function. The sum of the concave functions is a concave function. Maximizing concave function, we know how to do it. It's a convex program. Okay, because concave functions have kind of unique maxima, and that's why it's kind of the set of max is going to be convex. So this is very nice. It's going to be global optimum. We can find it. Blah blah blah. Okay, and that's why it's kind of solved since 1959. Okay, but the red guy is kind of difficult because you are minimizing a concave function and you have an open constraint. Okay, but the point is that we are not after global optimum, we are after local optimum here. So they show that in this program, you need not find a global optimum, you just have to find a local optimum. Do you see my cursor when I'm moving it around?
Yes.
Yeah, okay, good. Okay. So the local optima, so because here the maximum, the global optima is going to be on the upper kind of border, but for the local, we are minimizing. So the minima is going to be on the lower border of the feasible set, right? And because it's a local optima, there are going to be many of them because it's a non-convex program for minimization. Okay, so if you, let's say, have a concave function and you say minimize it in some domain, they're going to be even in one dimension, there's going to be like 2 minima, right? So yeah, so there could be multiple local optima. Okay, but we also have to avoid these obvious minima, which are when one of the coordinates are 0, one of the di of xi is 0. Okay, so that also have to be avoided. So some kind of boundary has to be avoided. Okay. Okay, so this is where we are. Okay, so geometrically we are after a point on the lower boundary where, so what do you mean by a local optima? Geometrically, it just means that at that point, there should be a supporting hyperplane such that the normal to the supporting hyperplane should be proportional to the gradient of your function. What is the gradient of this function? Log of some x is 1 over x, right? So for the di coordinates, 1 over di. And so that's what gradient is 1 over d1, 1 over d2, blah, blah, blah. Okay, that's your gradient. Now, and I am talking in terms of like in the dissolution space. Okay, so I can convert allocation space to dissolution space using this just linear function. It's just linear transformation. Okay, so the local optima intuitively just means that you want to find a point on the boundary such that there is a supporting hyperplane going through it, such that the normal to the supporting hyperplane is proportional or after rescaling equal to the gradient of the function. Then it's a local optima. Okay. Why does it give CEI? Well, it needs some proof. Let me skip this proof. I'll share the, or should I go over it? Okay, let me quickly go over it. But if you don't get it, don't worry, because it's a little bit involved and I may have to go a little fast. Okay, so let's say P1 to Pm are the prices. What does, so now I'm trying to understand what competitive equilibrium is to relate it to this local optima. Okay, why this local optima gives us CEI. So you have prices, you have allocation of bundles. Every agent gets an optimal bundle at these prices. What does that mean? That means it must be the pain minimizing or dissolution minimizing bundle at these prices, given that each of them earn at least $1 or 1 rupee, right? Now, let's say, look at the pain per rupee they incur. So if Dij by Pj is the pain per rupee that agent I incurs from chore j, right? Now the agent doesn't have any restriction on what they can consume and what they cannot consume. Okay, so they are only going to try and consume the ones that gives them minimum pain per rupee earned, right? So minimum pain per buck, only those chores, right? So these chores. Given that they're only going to consume these chores, the dissolution is exactly going to be earning times the minimum pain per dollar. Okay, and so because each of their earning is 1, so essentially the dissolution at equilibrium has to be the minimum pain per dollar or minimum pain per buck that they get. Okay, so is this point clear that they're going to only demand those chores that gives them minimum pain per buck? Is that okay?
Thanks, so far so good.
Sorry?
Yeah, so far so good, I think.
Okay. So then, and then we also have to have that supply equals demand. So these two basically the point is that supply should be equals demand, and dissolution of every agent is going to be just minimum pain per dollar or minimum pain per buck. Okay. So now let's look at this point where you have a supporting hyperplane with grade normal equals gradient. Okay, so let's set Pj. So I have this gradient Ai. Let's set Pj equals minimum over all agent I, Ai times Dij. You will wonder why. Let me show you why. So if this is how I set the price J Pj, then I know that Pj is less than equals Ai Dij by definition. That means 1 over Ai is less than equals Dij over Pj. Okay, I'm just doing some math manipulations here, simple. So for every agent I know that 1 over I is less than or equals min over j dij by pj, right? Which is our minimum pain per buck for these prices, by definition. Now, using the supporting hyperplane property, we can show that 1 over ai is exactly, so this is not inequality, but this has to be exactly equality, minimum j dij or pj. Okay, and I'm not telling you why, but basically it just uses the fact that at this point, this ai dot d star, a dot d star is minimum. For any other point, it's more. Okay, using that, you can just prove that this has to be equality. That means 1 over ai is exactly NPBI. Okay, and because we have a KKT condition, because we have that di star is exactly 1 over ai. So you get di star equals 1 over ai equals mpbi equals, that means CEI, right? The property of CEI was you have to ensure supply equals demand, and the every agent's utility, disutility is their mpbi. That was the characterization I just showed you in the previous slide, right? So that's it. And when you allow approximate local optima, so where the gradient is approximately equals the normal, okay, you get that every agent is earning or spending 1 plus minus epsilon. That means here you're going to get this 1 plus minus epsilon multiplier here. That's it. Everything else remains the same. Okay, so that means that the earning is not exactly 1, but 1 plus minus epsilon between that. Okay, so approximate KKT gives you approximate CEI. Okay, good. So we are after local optima. Why not apply just gradient descent? Right? Gradient descent, whatever, doesn't care about whether the function is convex, non-convex. You can apply gradient descent to whatever method, right? Your set is convex, so this should be okay. The tricky part is the open constraint that we have, that every dissolution value should be strictly greater than 0. Okay, so if you want to minimize this function, the gradient is 1 over di, but because you are trying to minimize, you're going to move in the direction of the negative of the gradient. If you want to maximize, then you move in the direction of the gradient. If you want to minimize, you move in the opposite direction, right? Because essentially, like geometrically, what gradient tells you is to where in what direction function increases, right? So this is the direction of increase. Then you have to go in the opposite direction to decrease it, to decrease the function. Okay, so if you apply gradient descent, it's going to move in the minus of 1 over di direction. Okay, so the smaller the di is, it reduces the fast. But then the minimum coordinate, so where will the minimum coordinate is going to reduce fastest. Okay, so what would happen that when you apply this gradient descent, even if you, let's say, add barrier functions, log barriers, so people do this to avoid boundaries, but whatever you do, we did experiments, whatever you do, it will take you to one of the coordinate to 0. So it will basically pick the kind of the least coordinate and decrease that all the way to 0 when you apply gradient descent. Okay, so that was main issue, and then okay, so then we thought that what to do. So one observation we saw was that anything that is local min from the inside is going to be local max from the outside. And I'm defining the exterior region in a particular manner. It's the region below the lower hull. Okay, so anything that is max a local min from the inside, the gray region, is going to be a local max from this exterior region. Now the issue is that this exterior region is non-convex. Okay, but still this property holds. Okay, now if you try to maximize from this exterior region somehow, okay, then you will move in the direction of 1 over di, and now the minimum coordinate increases the most. And this is exactly what we want, to move away from the 0 boundary. Okay, so we want to avoid any of the di's becomes 0, and this is perfect moving in 1 over di direction, because the minimum coordinate is going to increase the fastest, right? So this gives us an approach. The issue is that we are in a non-convex region. How do you kind of really show convergence, and on top of that, how do you show fast convergence? So we show convergence through a potential function. We show that this function that we are trying to minimize from inside is a potential function when we try to maximize it. In particular, we show that let's say start from any exterior region E and project it to the boundary of your feasible region. Okay, so this D is the nearest point to E. First thing we prove is that D has to be coordinate-wise larger than E. And it's kind of intuitively clear here from the geometry of the regions. Okay. This means that when we go from E to D, this objective is increasing because coordinate wise, you are increasing the point. Then you take the supporting, because there's a boundary point, there has to be a supporting hyperplane. You take the supporting hyperplane, and on this supporting hyperplane, now you explicitly maximize this objective. Supporting hyperplane is a convex region, it's just a hyperplane, and you just have to maximize this concave objective. So you're good, you can do that. Because you're maximizing, it must, if it moves, goes to some E prime point, that's your optimum, then D, then you must have increased the objective strictly. Right? So when you do this maximization on the supporting hyperplane for this objective, if you go from D to E prime, it must be that E prime has larger objective for this than at D prime, than at D. So you strictly increase the objective. Okay? So this gives us a potential function. But we still have to show fast convergence. It may happen that the potential is increasing very, very slowly. Okay. And recall that we are after a point where the normal is proportional to the gradient, which is 1 over D. So the whole method is this: you start with arbitrary exterior point, it's easy to compute. Okay, then you project it to the feasible region, the nearest point. Okay, we can show that this direction from EI to DI is going to be your supporting the hyperplane to the normal at the supporting hyperplane for the DT. Okay, and you stop when this normal is proportional to the gradient at DT. Okay, if not, you continue. You go on the supporting hyperplane to the point where this objective is maximized. And now this is going to be definitely giving you another exterior point, because supporting hyperplane touches the feasible region, intersects the feasible region only at that point, or that hyperplane of that point, right, of the feasible region. So you will end up at a boundary point when you do this maximization, or at an exterior point for sure. Okay, and you can keep doing this until you reach a point where your normal is proportional to the gradient. The question is, for sure, the potential is kind of decreasing. So you have to kind of at some point, well, need not stop, because there are infinitely many points you can go to, right? So we have to show kind of a convergence and a fast convergence for polynomial time. Right, so we keep doing this until you find this. And recall that we are after only approximate KKT. So if a point, I don't have to have like A is exactly 1 over D, but A is 1 plus minus epsilon 1 over D, right? Okay, so we already showed these two lemma, that KKT, approximate KKT gives approximate CEI, and this is a potential function. In top of this particular lemma is most important. We show that the potential increases if you are not at an approximate KKT point, then the potential increases by at least epsilon square over n square, right? If not, then you must be at approximate KKT point. An approximate KKT point gives you approximate CA. Okay, so these three lemma together gives us the final theorem. And basically, let me not go into details of this particular lemma. That's the most involved and technical lemma, so I'm not kind of going into details of that. But any question about the algorithm or about the approach?
No question.
No? Oh.
Okay. Generally, do put them in the chat or use the raise hand option.
So there is nothing in the chat? Right.
None.
Okay. Okay, and then we do a lot of technical thing to extend the result to one homogeneous. I don't think, I mean, I can tell you what it is, but it's for this particular talk, it's okay. I think basically what I wanted to tell you was about what is competitive equilibrium, why it is important for fair division, and this one method that we develop for dividing chores. Okay, so when we go to one homogeneous, the first obstacle is that the function is not given explicitly. It's an oracle access to the function, because we are allowing arbitrary one homogeneous functions. And so then the space of feasible dissociative values or plane values is not convex. We have to make it first convex, and it's not easy to find. Each of the steps become really complicated, finding the nearest point. In each of them, you're going to incur errors, and you have to handle all of those errors. And then more importantly, we can kind of extend this to a weighted case where agents have different powers, let's say. So WI is the weight of agent I, or you can think of WI is the amount of earning that agent I has to make, and also to mixed mana. And as I said, in the mixed case, you have to first identify whether the instance is positive, null, or negative, and accordingly kind of decide what their earning or spending should be. And then you can apply known algorithms. We show that you can apply the known algorithms to handle each of these cases. Finally, let me just kind of finish with another type of model that people study, which is called barter system. This is more basic than actually the markets that we saw. This barter system was the first type of market that happened in the world, right? So it's like, I give you milk, you give me bread, barter. Okay, there's no money involved as such. So let's say Wij is the unit of chore j agent I has, or good, if you wish, if it's a good system. And then this is the starting amounts, and then they want to exchange among themselves to improve their utilities, basically. Okay. And in the chores case, you would wonder where would barter happen? Well, in many cases. So in Germany or in the West, there are systems between elderly and young people where they share accommodation. So elderly people let the young people stay with them when they are studying or whatever, and the young people in exchange help them with their chores. Okay. There is something called time bank. You can look it up, timebank.com or org, whatever, where people do each other's chores. They earn time credit, and they can use time credit to ask or request others to do their chores. Okay, so it's kind of a community system, or students teaching each other or whatever, right? And then when here we allow that every agent cannot do every chore. Like if you ask me to teach a course on music, definitely I can't do that. Okay. So it's not that in whatever the chores are there in the system, everybody can do everything. That's not true. So if you allow that, then we show that in the exchange model, first of all, equilibrium may not exist. And secondly, we have to checking if there exists an equilibrium is NP hard, even like constant approximation. And these are all, these slides are basically for the yeah, I mean, people who are doing already computer science, then only they'll kind of understand what these NP hardness and all this stuff are. And then there are some conditions that we have to assume under which equilibrium exists. And this was the interesting part, that under some mild condition we can show that the equilibrium does exist. Okay, so actually the most important condition is that you can divide people in the groups, that this group of people can do these set of jobs. Like you can say that all the faculty in computer science probably can teach courses in computer science. Like if you give them enough resources, probably if you give me enough resources, maybe I can teach a course on compilers. Okay, I can try. Okay, but definitely not a course on music, something like that. Okay, so then the equilibrium exists, and yeah, so there are main difficulty is about a zero price bundle. But yeah, let me not go into that. Let me kind of finish with open problems, because I want to kind of I want you guys to get excited about this problem and maybe think about it. So the computation in exchange market is kind of open. If you allow the DIJs to be some infinity, that means some agents cannot do some chores, then it's hard. But if you don't allow that, so if all the DIJ values are finite, then we don't know what the complexity is. And let's say This time I gave you approximation algorithm. What about exact algorithm? What's the complexity? Not clear. Okay. Yeah, and there are still typical approaches used for the goods case horribly fails for getting exact algorithms. Okay. Okay. Yeah, so we did get a combinatorial algorithm, but again for approximation. Okay. And this gives us some kind of separation between CEI and exchange, but we still don't know the algorithm for exact. So these are still remains like open question. Okay. So you can also think of other strategic aspects, that if people lie about their value, then how much is the loss and so on. But I think the computational questions are more interesting, that how do you get a exact algorithm which is polynomial, or what is the complexity of exchange model. And these are my amazing collaborators on this work, and I thank them, and I thank you for listening to me and for this opportunity. Yeah.
Thank you very much. This was, I think, it was a really great lecture. So if there are any questions, do write them out in the chat. Or yeah, Naman.
Yeah, ma'am, I have a question. So this work largely dealt with like basically when the utility functions were one homogeneous and when they were convex, right? So has there been work done on more general utility function?
Good, very good question. So yeah, so there are many different ways to generalize one homogeneous, right? You can go to, let's say, Gauss substitute and so on, but you can also go to, let's say, separable concave utility functions, which is you still have a concave utility function, but you can separate it across goods. So you have, let's say, one concave utility function for ice cream, another concave utility function for chocolate. And when you get both ice cream and chocolate, you see how much utility you get in both the function, you sum it up. Okay. So for those are also very well studied for the goods case. For those, it's hard. But this is the only extra result we know beyond unhomogeneous.
Okay, thank you.
I think on line similar to Naman's question, how realistic are the assumptions, say the inhomogeneity and things?
The homogeneous allows you to, so what is homogeneous? Homogeneous meaning f of alpha ax, where a is a constant, is a of f of x. Okay, so this lets you use that characterization of BMSY. So BMSY characterization holds only for the one homogeneous functions. Okay, if you go beyond one homogeneous function, that characterization, that minimizing the product subject to open constraint, doesn't hold anymore. Okay, so that's why, and also this Eisenberg-Gale convex program is applicable only to homogeneous. So this comes from when you try to write the optimality condition for these programs. How do you? Okay, so I never proved to you that these programs indeed gives you a competitive equilibrium. Right? I just told you that if you solve this program, then you get competitive equilibrium. You should have asked why. Right? Because in these programs, there are no prices. First of all, there are no price variables, only allocation variables. Right? How do you get a competitive equilibrium from this? Optimum of this. So you write the KKT condition, the dual variables are going to give you prices. Okay, and only when the function is one homogeneous, you can exactly map the KKT condition or the optimality conditions to the competitive equilibrium conditions. Okay, so that's where the one homogeneous condition plays the role, and it's crucial. So beyond one homogeneous, this characterization breaks.
So if there are any other questions, do feel free to write to us, and we can definitely get them answered. So I think we understand some parts of the talk may have been a bit too technical to some of you, but I think the ideas introduced are definitely indeed extremely amazing. So do join me in thanking Professor Ruta for this wonderfully structured lecture, how we started off with motivating examples right from daily life and building up the pace, and very soon ending up at open problems. So it was amazing to see how things all fell into place, and thanks very much for that.
Thank you.
Yeah. So we now meet at 4 p.m. tomorrow when Professor S. Akshay of IIT Bombay will be talking about Amik.
Yeah, so tomorrow we will be joining at 4 p.m. for a talk by Professor S. Akshay of IIT Bombay, and he will be talking on formal verification. He will introduce what is formal verification, and it is quite similar to what we not quite similar, but something on the same lines of what we saw today in the talk by Professor Prahlad Harsha. So hope to see you all there, and thank you, Professor Ruta, once again for taking your time out and talking to the participants of STEMS 2022 final exam. Thank you once again.
Sure. Thank you. Thank you, everyone.